Hello everyone, welcome to Rhodes Academy. In this tutorial, we're going to continue in our complex number series by looking at the polar representation of complex numbers. In previous tutorial, in the last three tutorials, I think we've looked at the modulus of a complex number, we've looked at the conjugates, we have looked at the argument also, and we've looked at the Argand diagram, which is the complex number graph. So we are going to be using these three parameters, these three knowledge, to find the polar representation of our complex numbers. So if you don't have ideas about modulus, about argument and Argand diagram, I would advise you check those tutorials on modulus of a complex number, argument of a complex number, and also the Argand diagram. I've just moved straight to what we're supposed to do today, which is the polar representation of a complex number. So we've known that we are expressing our complex number z in terms of x plus iy. I'm going to mention this again. Maybe you have the x to be the real part of the complex number and the y to be the complex part of the complex number, and I, as we know, is our complex number. So we can express this complex number in its polar representation if you can find the r, which is the modulus. So we are going to need the r, which is the modulus, and we're going to need the theta, which is the argument of the complex number. So if you can find the r and the theta for this complex number, then we can find the polar representation of the complex number, and it's defined as z to be equal to r cos theta plus I sin theta. So we have z equal to r cos theta plus I sin theta. There are some other terms I will later introduce in this tutorial, or probably in the next one, concerning the what they call the De Morvis theorem and also the Euler's theorem. So we can also represent our complex number in those terms too. We have the length of this to be r. So what you can do is to bring this downward, and we call this theta. So from this triangle, we know that cos theta, let me write this here, cos theta equal to x over r. So from here we know that if you cross multiply, we are going to have x to be equal to r cos theta. Take note of this first. Also from here we know that sin theta equal to y over r. And from here we have that y equal to r sin theta. The proof is really simple. So we have that x, we define x as r cos theta, and we define y as r cos r sin theta. So from this representation that z equal to x plus iy, we can then substitute the value for x and for y. So if I'm to write this again, I'm going to have z to be equal to x is now r cos theta plus I, and y is r sin theta. So since we have z, or we have r to be common terms, we can factorize r out, and we have r into bracket cos theta plus I sin theta. So this is the proof for the polar representation of our complex number. Z equal to r into bracket cos theta plus I sin theta. So whenever you have to represent a complex number in its polar form, we simply need to look for r, which is the modulus, and also we look for theta, which is the argument of the complex number. Now let's look at some examples. Okay, we have our first example. The question says, given that z1 equal to 2 plus 3i and z2 equal to minus 3 plus 4i. Find the polar representations of z1 and z2. This is quite simple to do. We just have to find the modulus and find the argument in the case of z1 and case of z2. But one thing I want to point out to you is what I said when we were doing tutorial of, that is argument. Yes, that before you can find the argument of a complex number, it's very important if you can draw out if you can draw out the graph of the complex number, that is the complex plane. It's going to help you in finding your theta, because as I mentioned that time, that theta, which is the argument of a complex number, is always measured with reference to the positive real axis. It's always measured with reference to the positive real axis or the positive x-axis. So we're going to be looking at that same fact in looking for the polar representation of a complex number. So let's start. I hope with this example you are going to understand this better. So the first one, so is z1. So z1 is defined as 2 plus 3i. Don't forget, as I mentioned initially, if you have to find the polar representation of a complex number, you are going to need two things. Let me clean this. So that is the modulus, and that's the r, and the argument. So that's theta. So first and foremost, if you have to find the r, which is the modulus of this complex number, you're going to have r equal to, if you don't understand this concept, you can check my tutorial on the modulus of a complex number. So this is 2 squared plus 3 squared, and then we have this to be equal to the root of 13. And in finding the modulus, as I mentioned, let's plot a graph to represent the complex number z1. So we have, from our representation, we have 2 plus 3i, so they are both positive. Therefore, our complex number is in the first quadrant, which is in positive x and y axis. So we have, this is the r, this is 2, I have 3i. So we're going to have our theta to be this angle, and this is tan inverse of 3 over 2, and this is 56.3 degrees. So we have theta to be equal to 56.3 degrees. So with these two values, we can write the complex number z1 in its polar form. So we now have z1. So let me rewrite the formula. So guys, we have that z1 equal to r cos theta plus I sin theta. So this is the formula we are using. So we have z1 to be equal to, in this case, our r is root 13, cos theta is 56.3 plus I sin 56.3. So this is the representation of complex number z1 in polar form. Root 13 cos 56.3 degrees plus I sin 56.3 degrees. So that's that concerning z1. Now let's look at z2. So number 2. So we are defined. So z2 is defined as minus 3 plus 4i. So as always, the first thing we have to find is the modulus, which is the r. This is negative 3 squared plus 4 squared. And here we have that r equal to 5. So to find the argument, which is theta, so let's draw the complex plane. So if you look at this complex number z2, we see that we have negative 3 plus 4i. So the real part is in the negative part of the graph, which is negative 3a, and we have 4i. So let's define this as a complex number, and we have ra. So I have this. So if you have to measure theta, we have to measure from the positive real axis. So this here is our theta. So but we can't find this directly, so I'm going to find beta first. So we define beta. It's going to be the tan inverse of -4 we can put -4, but I'm going to remove the negative sign since we're only looking for angle beta here. So we have beta equal to tan inverse of 4/3. So this is opposite is 4 and the adjacent is 3. Opposite of 4, just like we have for the y-axis, and the adjacent is 3, like we have for the x-axis. So we have beta to be tan inverse of 4/3, and from here you have that beta is going to be equal to, so I'm going to use my calculator to find that the tan inverse of 4/3 is 53.1. So you have beta to be equal to 53.13. And now if I'm to find angle theta, don't forget that the sum of angle on a straight line is 180 degrees. So finding angle theta, now we're going to have theta to be equal to 180 degrees minus 53.13 degrees. And now I have my theta to be equal to 126.87 degrees. So having found theta, we can now write our complex number in polar form. So we have Z2 to be equal to R. So R in this case is 5. Cos theta, don't forget we are not going to use beta, as I mentioned initially, that the argument of a complex number is usually measured with reference to the positive real axis. So even if the complex number is here, you have to measure that from positive real axis to this point. So we already considered that while we're looking at the argument of a complex number. You can check the last tutorial to learn more about this. So you have cos theta is 126.87 degrees plus I sine 126.87 degrees. So that's that concerning this example, the first one and the second one. So given that z1 is 2 plus 3i and z2 is minus 3 plus 4i, so we derive the polar representation of z1 and z2. Now let's look at what if you have division, what if you have power, how do we handle that? So let's look at another example. Before I start looking at the multiplication in polar form and also division in polar form, I like to talk about the properties of polar form because this is going to help us in multiplication and also in division. So the first one we are going to, let me change this a more vibrant color. So the first one we're going to look at is that, but before I write the first one, let me just give us the condition we are going to be considering. So if you have complex number z1 to be equal to r1 cos theta 1 plus I sine theta 1, and z2 to be equal to r2 cos theta 2 plus I sine theta 2. So the following properties is going to hold true. The first one is that z1 multiplied by z2 is going to be equal to r1 r2, this is r1 times r2 cos theta 1 plus theta 2 plus I sine theta 1 plus theta 2. When I was introducing this tutorial in the last tutorial, I talked about that if you are considering polar form of complex number, it's going to help us in multiplying complex number. Just imagine if you have a complex number, if you can get the modulus and also the argument, you can easily multiply them by just multiplying the modulus and adding the arguments. The same thing is applicable if you're looking for the division of the complex number. If you have z1 divided by z2, it's going to be equal to z1 this will be r1 for r2 cos. So instead of having addition, we are going to have subtraction. Yeah, theta 1 minus theta 2 plus I sine theta 1 minus theta 2. So these are the two properties we like to consider: division and also the multiplication. There are some other things that it's possible that quite things to do, which is power. And it's even more simpler to do power and also do addition, subtraction, multiplication, and division if you're considering the Euler's formula. I'm not going to be dwelling much on this. I'll just do some kind of quick overview of what the Euler formula is. If you want to learn more about Euler, you can read more about that. Wait, let me just put Euler here. So he defined the complex number. This is just like a formula. It's done e to the power of I theta to be equal to cos theta plus I sine theta. So e to the power of I theta equal to cos theta plus I sine theta. You can do a whole lot of things with this. This can be represented in to become like polar form by adding r here. If you add r here, then you have to add r here, then you have to add r here. So if you can express a complex number in this form, then you can easily do multiplication. For example, if you have r1 e to the power of I theta 1 multiplied by r2 e to the power of I theta 2. So this will go by the law of indices. It's going to be r1 r2 theta, no, that is e to the power of I theta 1 plus theta 2. So it's going to make your work a lot easier if you're working in Euler, but we're not going to be looking at that in this tutorial. Also, if you're doing division, if you're doing power, you can easily work with Euler's formula, then you can later convert to a normal polar form. But that's not what we're going to be looking at in this tutorial. It's just a quick overview of what the Euler formula talks about. So let's go back to our polar form. If you look at the first property and also the second property. So we're going to be using these two properties to find the multiplication of a complex number and also the division of a complex number. And let's start with some examples. This is the last example we are going to be considering for this tutorial. And the question says, given that a equal to 2 root 3 minus 2i plus and b equal to minus 1 plus square root of 3i, obtain the polar representation of a and b and find a. Oh, this is supposed to be a multiplied by b and a divided by b in polar form. So number 1. Our first task is to find the polar representation of A and also the representation of B. If you have already looked at this, how to go about this in the previous example, I'll just do a quick run through of it. So, no. So we have A is giving us 2 root 3. That's negative minus 2i. So here we are going to have our r to be equal to 2 root 3 square plus negative 3 square, and this equals to 4. Also, to find the arguments, we are supposed to withdraw we are going to draw the Argand diagram. So we have our complex number to be in this axis. So this is 2 root 3 and this is negative 2. And here we have our r. So our theta is measured from the positive real axis. This is theta, and we can name this beta. So from here we're going to have that beta equal to the tan inverse of 2 all over 2 root 3. And then we have that beta equal to 30 degrees. So to find our theta, we are going to subtract 30 from 360 degrees. So we have theta to be 360 degrees minus 30 degrees, and this is 330 degrees. So we have theta here to be 330 degrees. So from here we can say that A is going to be equal to r. R is 4 cos theta is 330 degrees plus I sine 330 degrees. So this is representation for A. Also, let's find the representation for b. B is defined as b equal to -1 plus root 3i. So from here we have that r equal to the root of -1 square plus root 3 square, and this equals to 2. So the next thing to find, just like in the previous one, is to find the argument, and then we draw an Argand diagram. So if you study this complex number, we have the positive I, positive imaginary axis, and negative real axis. So we're going to have complex number in this. The complex number is in this quadrant. So coming down, here we have our -1, and then we have root 3. So we can name this are theta, and this can be beta. So from here we are going to have beta equal to the tan inverse of root 3 over 1, and we have beta to be equal to 60 degrees. So to find that theta here, just like we did in the first example, we are going to have theta to be equal to 180 minus 60 degrees, and this is equal to 120 degrees. So with this we can write that b equal to r, which is 2 cos 120 plus I sine 120 degrees. So you have represented A and B in polar representation. So our next task is to find A multiplied by B. So we have to find A multiplied by B. And before I write this, let me write out the formula we are going to be working with. From the properties, we know that Z1, Z2 is going to be equal to Z1 multiplied by Z2 cos theta 1 plus theta 2 plus I sine theta 1 plus theta 2 plus I sine theta 1. So we're going to be using this formula here, Z equal to Z1 multiplied by Z2 cos theta 1 plus theta 2 and I sine theta 1 plus theta 2. So what is R1? This is 4 multiplied by 2 cos we have theta 1 to be 330 and theta 2 to be 120. So plus I sine the same thing, 330 plus 120. And from where we have this to be equal to 8. You find the cos of 330 plus 120, that is 450. The cos of 150 is 0. And the sine of 450 is 1. So you have the full answer here to be equal to 8i. So that's a polar representation of A multiplied by B, which is 8i. Also A divided by B so this is going to be equal to A divided by B. So instead of asking theta 1 plus theta 2, just like we have here, we're going to have theta 1 minus theta 2. Theta 1 minus theta 2. But instead of that, I'm going to substitute alpha low in there straight. So you have 330 minus 120 plus I sine 330 minus 120. Also, I'm going to substitute for A and B. So you have A to be equal to 4 and B to R1 to be 4 and R2 to be 2. So here we have 2. The cos of 210 is negative root 3 over 2. And this is also negative 1 over 2i. So if you multiply 2 to open the bracket, we're going to have negative root 3 minus 1i. And this is the same thing as root 3 minus I. So these are representation of A divided by B. And we have the polar representation here, and we have the complex number here. Same thing in this case. So that's that concerning the polar representation of complex number. We've looked at how to represent complex number in polar form, how to perform subtraction, and how to perform multiplication, and how to perform division. So in this video, we're going to be starting with the root of a complex number. So see you then, and bye.